Hi, everyone. Welcome to this online tech talk where we will discuss how Simulmedia uses Amazon Redshift to scale their analytics and bring richer advertising experiences to their viewers. My name is Vaidi, and I'm part of the analytics specialist team here at AWS. And joining me today is our customer speaker, Amardeep Singh, Vice President of Engineering at Simulmedia. We hear from customers all the time that they're looking to extract more value from their data, but they struggle to capture, store, and analyze all of that data to drive insight in a scalable fashion. Data is growing exponentially today, and it's coming from new sources. It's increasingly diverse, and it needs to be securely accessed and analyzed by any number of applications and people. And our customers tell us that they're struggling with the large volumes, velocity, and variety of data. They have challenges of performance and concurrency. They have multiple analytics choices. There's different ways in which they want to analyze data and how they want that information to be surfaced, from KPI dashboarding to ad hoc analytics to real-time and operational analytics and predictive modeling. And they want to do all these things in a secure and compliant way without incurring the burden of self-managing legacy analytics infrastructure, which can be costly and inflexible. And at AWS, we have a broad and deep portfolio of data lake and analytics services that addresses these challenges. This portfolio is cloud optimized from the ground up. It's purpose-built in that we have specific services that are aligned with the specific jobs you want to perform, from data movement to historical reporting to machine learning-based predictive analytics. A one-size-fits-all approach, we believe, no longer works, as customers often have to trade off functionality, performance, or scale when they do so. And it's fully managed, taking away all the burden of undifferentiated heavy lifting and allowing you to focus on driving insights that will improve your business. And the focus of today's presentation is Amazon Redshift, which is our purpose-built service for data warehousing and addresses the needs of analyzing modern data at scale. Redshift does this by allowing you to combine traditional data sources in your data warehouse with event data sitting in an object store like Amazon S3, as well as real-time data stored in a transactional database such as Amazon Aurora or Amazon RDS. And we call this approach a lakehouse approach, where you can use a single interface to query a set of tables that virtually maps to where the data resides, whether it is your real-time streaming data landing into S3 in CSV or Parquet format, or transactional data that is being loaded in real time into a Postgres database like Amazon RDS or Amazon Aurora. And our unique value proposition here is that you do not have to load all of that data into Redshift to be able to query and access it. We provide a query federation model that allows that data to be local to Redshift. It can be in S3 or it could be in Postgres. But as an analyst, you just see tables and schemas, and you can simply interact with the data as you please. And as a data engineer, you do not have to do the heavy lifting of moving that data around. And you can rest assured that your business user stakeholders can simply query the data in place, whether that data is historical, real-time, transactional, and develop a unified 360-degree view of the business. Let's now talk about Amazon Redshift's benefits that are being leveraged by tens of thousands of customers across the world. The first is how we integrate with the data lake and other AWS services, where we're able to use lake formation for centralized security and cataloging, AWS CloudWatch for monitoring, DMS for ingesting data, and all these capabilities are seamlessly integrated with Redshift to allow you to deliver the full power of AWS analytics to your stakeholders and customers. We also deliver the best query performance across a variety of use cases. We have gathered this from customer feedback and proven this in the TPC-DS synthetic benchmarks we've run against other players in the market that allow us to assert that we're 3x faster than any other cloud data warehouse, and we are 2x faster versus where we were just 6 months back. And this is performance out of the box with no tuning whatsoever, although we do provide knobs and optimization levers to make Redshift go faster in your scenario. And we provide this performance at the lowest cost of any other data warehouse. Our pricing model is on demand and pay as you go, but if your workload is predictable, you can take advantage of a unique billing construct we have called reserved instance that allows you to prepay for compute and benefit from anywhere between 30 to 60% off of on-demand rates, thus reducing cost variability that you might see with other solutions. And in delivering this low cost, Redshift is also the most scalable. With features such as concurrency scaling, I can confidently deploy Redshift not just to a fixed workload, but to a variable one, where the number of users might vary by time of day or day of month. And for what you pay, you also get the most secure and compliant data warehouse solution with third-party certifications like PCI, DSS, and FedRAMP, not to mention AWS-grade security with virtual private cloud isolation and encryption with KMS. And finally, Redshift is really, really easy to manage. We have powerful capabilities that remove the need to have dedicated resources looking at Redshift on a day-to-day basis. And this, of course, is further enhanced by all the machine learning-driven features we have introduced just in the last 6 to 12 months that make Redshift autonomous, self-managing, and self-optimizing. At AWS, we're on the forefront of data warehousing and investing in building Redshift for the next generation of analytics while completely rethinking architecture, use cases, and scale. Principally, there are 3 areas that we're innovating around. First is around performance and scalability. We have made tremendous strides in out-of-the-box performance driven by our analysis of usage patterns and direct customer feedback. In fact, over the past 18 months, the Redshift out-of-the-box performance has gone up by a factor of 3x. And all of this, by the way, is without any tuning. This increase is on top of the 3x to 5x performance increases that customers have benefited from over the course of 2017. And all the while, we have not increased prices. On the contrary, we have built capabilities like pause and resume and cost controls for concurrency scaling that help you reduce your bill while you see improvements in performance and scale. Second, we're building more data lake integration for security and access control to leverage the scale of data lakes and different processing engines. Redshift remains the only cloud data warehouse that integrates directly with S3 by allowing you to run ad hoc queries against data in S3 in open formats with no loading required. And finally, we continue to invest in capabilities that make Redshift easy to use and self-optimizing with auto management capabilities like auto WLM and auto vacuum. Thanks to all these innovations, Redshift today is by far the most popular cloud data warehouse with tens of thousands of customers across industry and geography, covering the gamut from the largest enterprises to the most cutting-edge startups. And together, these customers, they leverage the power of the lakehouse as well as the native capabilities Redshift offers to provide analytics at scale to their organizations. Now, one particular innovation that I want to talk about that will be the focus of the presentation today and what Amardeep will cover is a brand new RA3 instance that we launched at reInvent that we've seen significant adoption around. RA3 with managed storage allows you to scale and pay for compute and storage independently, allowing you to size your cluster based only on your compute needs. It's built on the AWS Nitro system and features high bandwidth networking and a performance indistinguishable from bare metal. RA3 nodes use very large high performance SSDs as local caches. They leverage your workload patterns and advanced data management techniques such as automatic fine-grained data eviction and intelligent data prefetching to deliver the performance of local SSD while scaling storage automatically to S3. And they remain fully compatible with your existing workloads. Our initial performance statistics that we have unraveled from benchmarks and from customer feedback tell us that compared to the storage optimized DS2s, RA3s deliver 2x more performance and 2x more storage capacity. And compared to the compute optimized DC2s, they deliver 8x more storage capacity. And we have seen tons of customers who have moved to these RA3 instances with tremendous success, and several of those customers are using these RA3s to drive marketing analytics use cases. These include customers like Playrix, Duolingo, and our next presenter for today, which is Simulmedia. And with that, I want to introduce Amardeep, who's Simulmedia's VP of Engineering, for the next part of the presentation. Amardeep, it's all yours.
Thank you, YD. It's great to be here with you to talk about Amazon Redshift. We've been using it for many years now, and our business has scaled in that time. Our needs have increased in that time, and I'll walk us through what we do, why Amazon Redshift is an important part of our technology stack, and why it's really helped us scale our technology and our business. So a bit of a background on Simulmedia. We take a data-driven approach to TV advertising. It's a big component of our product and our service is utilizing data to answer a fundamental question. And that question is, who's watching TV? What are they watching? And when. So essentially, who watched what, when on TV. By answering that fundamental question, we're able to target very effectively on TV using demographic data on TV viewers. By answering that question, we are able to build sophisticated forecasting models that allow us to deliver that targeted advertising in a highly precise manner. And also, once an ad actually airs on TV, we're able to measure its effectiveness. So all stemming from that fundamental question about who's watching what on TV, whether it's sports, whether it's sitcoms, whether it's kids programming, whatever it may be. If you can reliably answer that question, it allows you to take a fundamentally different approach to TV advertising and really be efficient about how you achieve your clients' goals. Our move to AWS really started about 6 years ago. What forced us to look at AWS was that our needs were changing. We were previously on an on-premise data center, which was failing to meet our needs, and the expenses were increasing, and it was largely difficult to manage. We had staff dedicated to the maintenance and management of our on-premise data center. We were running a large Hadoop cluster to do many of the operations that we now rely on Redshift for. And we would suffer hardware failures. We would suffer routine upgrades, which were challenging, and also Hadoop presented its own challenges in terms of ease of use. So we were looking for alternatives. We were looking for a cloud-based solution because not only did we want to get off of Hadoop, we wanted to get off of on-premise. We wanted to move to a cloud-based solution and a cloud-based data warehouse that could replace Hadoop. And the reason we chose Redshift is because of low total cost of ownership. And this includes things like hardware failures, the staff dedicated to managing things like hardware failures and upgrades, automated backups, integration with other cloud-based services like S3, having access to a service like S3, which is effectively unlimited storage, that's easy to access and scalable, is incredibly valuable. The distributed architecture, that was an area we couldn't compromise on given the data volumes that we work with. It's why we initially chose Hadoop, but we needed something that was more fitting to our needs than Hadoop, but still retains that distributed architecture to allow us to scale. A SQL interface. A SQL interface to a data warehouse or data processing platform is essential. SQL is the standard for working with data, and we needed something with SQL interface and a robust SQL interface. And finally, transactions. Transactions are sometimes an underappreciated area of data warehousing, but they're really powerful in what they allow you to do, especially in terms of modifying data in a consistent way, in a way that minimizes the impact on the consumers of that data. So Redshift really fit all of these needs, and we chose to move to it 6 years ago, roughly around the time when Redshift was first introduced. The core data challenges that we have at Simulmedia are that we have TV viewing data from millions of households. This is anonymized data, but the scale of that data does present a fundamental challenge to our product and to our technology stack. In addition to that, we have numerous ancillary data sets that we use to enrich that core anonymized viewing data set. So things like programming information and demographic characteristics and many others, ancillary data sets that really help us enrich that core data set. In addition to that, we have a data science team that is working with cutting edge tooling in the machine learning space that we need to be able to support and integrate more closely with those tools and platforms so that our data science team can continue to do their work efficiently and effectively. And maintaining multiple environments. We have product development teams that rely on Redshift, and for efforts like development, QA, UAT, we need to maintain multiple environments with different levels of prod-like data that can be used in those development efforts. So maintaining those multiple environments, ensuring that they have reliable data that resembles production level data, both in volume and quality. The first of these challenges, the anonymized TV viewing data from millions of households, is largely represented as a time series, and you can represent it as in other forms, but we find that a time series representation best fits our needs. And we found that distribution and sort keys are really essential here. Compression itself also really important in lowering the cost of storing this data, but also increasing the performance of querying this data. We found that time series data compresses particularly well, often achieving greater than 50% compression ratios. Also, it's fairly easy to archive, so you can take data that's some number of years old and archive it to S3, archive it to different layers of S3 storage, Glacier, for example, if you don't anticipate regular access to it. And we've also found that classical data warehousing techniques continue to work well in this distributed architecture. A dimensional data model comprised of fact and dimensional tables works really well. The biggest challenge here is querying it efficiently. TV viewing data from millions of households actually translates into many millions of events per day. And on particularly high activity days like sporting events or weekends, you can see it's not unusual to see hundreds of millions of events processing through our system every day. So given these volumes, querying it efficiently is really the biggest challenge. Our ancillary data sets are also another important challenge for us. This is generally dimensional data. It comes to us at different points in time. It comes to us from different source systems. This is sometimes referred to as late arriving data in dimensional data modeling and data warehousing. There are complex, disjointed data points here. And also, in addition to arriving at different points in time, sometimes requires reprocessing because the source systems have issued an update, and that translates into downstream reprocessing requests within the data warehouse. So all of these challenges really make data modeling and ETL particularly difficult. And some of the use cases that I'll talk about in the upcoming slides really make the data modeling even particularly more difficult because we're not able to push a lot of the complexity that we have in our technology stack down into the ETL layer and pre-calculate some of those operations because of the disjointed information and because of the varying points in time that it comes in. We're not able to pre-calculate those operations. So the particular challenge that we face in working with time series data is a problem that we internally refer to as an overlap analysis. Overlap analysis is a fairly common problem in different industries. There's different terms for it. It's sometimes referred to as a range join. And what it essentially means is that you're looking for overlaps between two events. It could be time series, but it could be something else. It could be a geometric overlap, and it can be represented in multiple forms. But for us here at Simulmedia, what we try to answer through an overlap analysis is that fundamental question that I referred to earlier in the presentation. What is playing on your TV? So here in the visualization that I have up on the screen, you have a few line segments. Now, each of these line segments actually represent different time series. The first line, the green line, is anonymized TV viewing data for, let's say, a particular TV. It has a start and end point. But between that start and end point, you might actually have multiple events that occur. You might change the channel. You might view multiple programs on the same channel. And that is the TV content that you happen to be viewing, and that's represented as the second set of lines in orange. And the last set of lines, the shorter line segments at the bottom there, are the ads that you might have seen over that time that you were viewing TV. So you may have viewed TV for 2 hours, and within those 2 hours, you may have changed channels and you may have watched different programs, and over that course of time, seen multiple advertisements. But reliably identifying what is playing on your TV allows you to have the building blocks to forecast what you may watch in the future. And our forecasting allows us to effectively place ads and target the right viewers. We use these same building blocks to measure the effectiveness of an ad once it does air. So let's break this example down further. Here you have a simpler example with just 2 line segments. The first one here illustrates 2 line segments with partial overlaps. The second visualization shows a complete overlap, and the third, no overlap at all. So this can be expressed in multiple ways. we found that expressing it directly in Redshift is the best approach for us because it allows us to push the computation down into the data layer without pulling it out of Redshift for further processing into an application or some other data platform. And the way that we've been able to push it down into Redshift, into the data layer, is through a really simple SQL statement. Now, this has been simplified just to illustrate how it functions, but you can imagine that you can have multiple time series here with multiple overlapping regions. But this specific example here, you have two time series tables, time series 1 and 2. And the join condition here, while it may appear to be counterintuitive, is accurate and it works. So the join condition is to find the overlap regions, look for the start points in time series 1 that are less than the end points of time series 2, and find the end points of time series 1 that are greater than the start of time series 2. So while it's counterintuitive, it actually works. It's correct. It will allow you to find those overlapping regions. You can test it against multiple time series. In a more realistic example, you would have additional join conditions. Perhaps there are keys that you can join on to narrow the space where you would need to perform this range join or overlap analysis type operation. But this is essentially it. This will allow you to find that overlap region between two time series or two line segments. The explain plan for this query actually is interesting because Redshift will warn you that this is a problematic query, that it needs to be reviewed because it is going to produce a Cartesian product. And in data warehousing or in big data spaces, Cartesian products are really problematic because what it generally means is that you are exploding your data set. A Cartesian product is no different than a mathematical product in the sense that 3 times 3 is 9. So in the same sense, you end up multiplying your data set very quickly if you happen to produce a Cartesian product. And that's exactly what Redshift is warning you about here. Furthermore, it's executed as a nested loop join. Of all the ways that a database, a data warehouse can execute a query, nested loop join is generally the worst. Just because what it actually means is that for each record in one data set, it will nest through each record in the second data set. So for each record in time series 1, it will nest through each record in time series 2. And in this explain plan, you'll see that for the sample tables I've created here, time series 1 has 18 million records, time series 2 has 365,000 records. So the performance here will be terrible. The solution to that is to really reduce the scan region or the scan space, and you can do it through multiple ways. So in this example here, the sample data that I've set up, time series 1 and time series 2, they both span about a month of data, September 2020. And there are no other keys to join in this case, but in a more realistic example, as I mentioned earlier, you are likely to have keys that you can join on to reduce the scan space. That will help with some of the processing because the keys that you join on will allow you to avoid some of those nested loop operations. However, you still are left with a fairly complex query that can perform terribly depending on the data set that you're working on. The approach that we have adopted to really help us make this query performant is to further partition the data set so that we're reducing the scan space even further. And the way we're able to do it is by understanding the fundamental nature of the data and what we are requesting of it, by understanding that viewing data, anonymized viewing data from a particular TV is unlikely to overlap with a TV content or TV advertisement that is some duration of time apart. So if you were viewing TV on a particular day and the advertisement or the content that we're looking to perform the overlap analysis against is on a different day, it is unlikely that you have been exposed to it. There are some edge cases that can happen, but generally it is unlikely. So if we can reduce the space, if we can partition the query further, you will see significant performance improvements. So in this example, over a month of data, if you can partition the queries to scan 1 week of data or 1 day of data or 1 hour of data, however you choose to partition the data set will allow you to realize significant performance improvements. So looking back over the past 6 years working with Redshift, we've increased our use of Redshift. We've regularly increased our cluster sizes as our data needs grow, as our use cases grow. And Redshift has really helped us scale our technology and business along the way. For some of the reasons that I mentioned earlier around automatic backups, hardware failures have been really essential here. However, the key technology within Redshift that's really helped us these past 6 years is Columnar storage. Columnar storage is the key feature that helped us scale. Given the nature of our business, large volumes of data processing, it made all the difference. So in this simple visualization here, I illustrate the difference between column-based storage and row-based storage. Row-based storage is how data is typically stored in databases, and what that essentially means is that each record, each row, is stored in its entirety in the storage layer of the database. And for you to perform an operation on that data set, aggregation type operation that is typical for our use case, if you were to aggregate 2 columns in this visualization here for row-based storage, the database will actually retrieve the entire record from the storage layer. This is very inefficient for large data volumes, for the type of operations that we do. However, in column-based storage, the storage layer is actually aligned to your use case and how you perform your operations. So the aggregations that you perform in any particular columns are actually aligned with the underlying storage layer. So it's highly efficient and allows you to execute complex, large volume queries very efficiently. Other important features that have really helped us scale over the years are compression. As I mentioned earlier, we've seen compression ratios in excess of 50% with some of our data sets. Workload management, really having fine-grained controls around how we prioritize workloads, how we prioritize applications and users, and how they utilize the underlying resources in Redshift. Spectrum has allowed us to take advantage of the flexibility it affords in being able to query data seamlessly within Redshift, being able to stitch together data sets that live within or outside of Redshift. Elastic resizing, when we need to resize our clusters, our environments to meet our changing needs, elastic resizing has been tremendously helpful. And the continued improvements in the Redshift instance classes. Over the years, there's a fairly regular cadence that Amazon releases these improvements, and we've taken advantage of them each time so that we can realize realize the performance improvements that generally come with them while maintaining the cost points, the cost structure. So it's been really helpful to be able to do that without significantly increasing our costs. And speaking of continued improvements to the Redshift instance classes, Amazon Redshift RA3 with managed storage has been a really important improvement that's come out this year. The most fundamental improvement is the decoupling of storage and compute. This allows you to plan for your compute needs only. Not only does it reduce your archiving needs, but it allows you to really combine the best of the previous generation of Redshift instance classes, the DS2s and the DC2s. When the RA3s were introduced, we tested the DS2 upgrade based on the recommendations from Amazon, and we were able to realize a 20 to 30% improvement for heavy ETL workloads, which represents the majority of our use cases here. And using elastic resize, we were able to do this within 10 minutes. And we're planning to upgrade all of our remaining clusters to the RA3 based on the experience we've had upgrading our DS2 clusters. And soon we'll be exclusively on RA3 because it affords us the flexibility on decoupling storage and compute, and also the general performance increases that we see here based on our tests. Now I'm going to pass it back to Vaidi.
Thank you all for joining the session today. For next steps, if you're already using Redshift, I encourage you to check in with your account team to continue to learn more about what's new and make sure you're taking advantage of the latest feature. There's a couple of different ways to do that. You can ask us for a free Redshift optimization session, or if you'd just like to be briefed on all the innovations that we've shipped in the last 6 to 12 months, we're happy to do that as well. I also want to direct our attention to this proof of concept playbook. If you're running a POC on Redshift, this document is going to be of tremendous help. We just launched it or launched the latest iteration of this playbook a couple of months back, and we've gotten some great feedback. And of course, we're also here to help. If you aren't sure who to reach out to, just request help from AWS with the link on the screen, and we'll make sure you are directed to the right team. Thank you everyone for listening again, and now we'll break for Q&A.